All right. Okay. Should be good. All right, and then if I have a web browser here, okay, cool. All right, so I guess we're ready to get started.
Everybody got
If you have like a Windows box, this might be, if you want to like walk through, it's the right HDMI plugged into the thing. Did we have
it was a minute ago here.
output on the slide, or was that?
It was working. Give it a second.
The other thing I've done is unplug it and then replug it.
No, that's not the one that's supposed to be plugged in. Try unplugging and replugging it. When in doubt.
Yeah. So now it's.
Yep, that's what it's supposed to be. Come on. We had it just a second ago.
Yeah. I can.
Try unplugging it there.
And I'm going to try and minimize the switching so that
yeah.
Hopefully this starts working and then works from there.
It's going wonderful.
Yeah.
It's not showing up there.
As far as
oh, it showed up for a second and then it went away.
It could be that it's like no.
Didn't we do it last time?
No, this isn't for the dot cam though.
Yeah, I know, but we were having issues with the laptop last time.
Really? Work your magic. I don't know.
Close some stuff in case of accidental. I think I'm on Do Not Disturb mode, so. As far as like, oh yeah, close out of KeyPass. That would be a good idea.
Wait, we're not using the dot cam yet though.
This is. This should still work. It worked last time. Try a different. Oh, you're this is fine.
Wait. Wouldn't this switch between? Okay, so the dot cam is the. I see.
Yeah, that's what I
so
did.
we were on the. Okay.
I did it because this works more consistently for some.
Cool. All right. Now.
Thank you for everybody online being patient.
Yeah, thank you
and
for-
everybody in person being patient while we did everything.
Yeah. How's the font size on that? Is that? Okay. Cool. So yeah, the main thing here, as far as like following along, is having access to some sort of Unix-like shell. So if you're on Mac OS, you can do it natively. If you're on Windows and have a VM, you can do that, or like WSL or something. All of those should work. But if not, it's also kind of just visual, so you can feel free to sort of follow along with the screen. But yeah, so there's some like setup stuff for getting these Jupyter Lab notebooks working. I'm gonna try and install them or have them installed on like a Python virtual environment, so that as far as I understand with virtual environments, everything is contained within the packaged Python environment within the virtual environment, so you're not like necessarily installing anything on your base machine. Well, outside of the virtual environment that you're using. So yeah, first thing to do would be to like actually, if you've downloaded either the tar or the zip from the links that I posted, go ahead and extract them, or well, I guess make your own directory, since these are just the tar files don't contain a directory. So go ahead and make a like directory to play around in. So crypto notebooks, and then move the .tar.gz. So move the tar file into that directory that you make, so that it's on its own. And then, yeah, it doesn't really matter where you do this in, but the main thing is that when there's like 8 files in here, so extracting it might be kind of messy otherwise. So yeah, any questions as far as like the process of you know, making a directory or setting things up, creating your own or moving the tar archive to your directory, or the .zip file if you're working on Windows, since I think the commands should sort of line up. Otherwise, yeah. Anyways, we go ahead and extract that, and then the command for that is tar tac xzf. The mnemonic for that is just extract z files. The other way is tar tac czf for compression. It's just, yeah. This will empty out the 8 file, or this will extract the 8 files in here to this current directory here. And yeah, so you can see there's a couple of .ipynb files. So we're going to install Jupyter Labs to sort of work with that. So since I don't really like the idea of having everyone install tons of stuff on their base machine, because then things get cluttery, the easy way to work around that is to use Python virtual environments. So the command to make a virtual environment is to call this module venv, and then specify a folder in which to create the virtual environment. And this will essentially copy a baseline Python 3 interpreter into that virtual environment, so that when you install, let's see, Python 3, the second argument is the module specifically, and the third argument, it doesn't matter what you use, but just specify a name for that virtual environment. And yeah, that will create its own sort of, there's like a Python interpreter inside that virtual environment, along with everything you need to run Python stuff. So you can install modules in there that are only active during that virtual environment and delete them afterwards to clean up, is the main thing. So to activate that, use the source command on notebook venv /bin/activate. Run that program, and that will redirect your path so that you're using the Python binary inside of that virtual environment. So you should have this sort of parenthesized prompt in front of your usual user at host stuff. The second one is because I also have Conda on my, or a different sort of Python environment manager on my machine, but yeah, you should just see this notebook venv thing. Yeah, there's a good bit of like setup here, but it's kind of a relatively easy install after this, because it's just using the Python package manager, pip. So now to install Jupyter Labs, and this should be installing it inside of the virtual environment as long as you have it activated, is just pip install Jupyter Labs, I think the one word, and that's with Jupyter with a Y. And I still pronounce it Jupyter, I guess, but this will install the, could not find a version that satisfies the Jupyter. Okay. Install Jupyter Lab without the S, I'm assuming. Yeah, okay. So that'll run through and install the mess of dependencies that is Jupyter Labs, because it's a pretty complicated application that runs a web server that's hooked into like actual kernel on the machine to evaluate code. I tried to sort of get I thought about getting a web server set up that people could just go to a browser and not have to worry about all of this on, but the prospect of doing that in short notice and having remote code access to that in a reasonably safe manner was a bit much. So yeah, I'm just distributing the notebooks. And then, so that installs the, after that's done, you should be able to run Jupyter Notebooks or a Jupyter Lab environment on your machine. And after that, pip install a couple more packages. The Python image library is used, which is Pillow, which is for like image processing and stuff. Again, you're installing it on the virtual environment, so yeah, just make sure, well, I mean, you could install it on your local machine if you want to also use Pillow later and do image manipulation stuff with Python, but otherwise, install Pillow and then matplotlib. Those two are modules that don't ship with the base directory.
Wait, what else in addition to Pillow?
Matplotlib. Also, yeah, I'll, let's see. 3 till what, 10? Is that the, yeah, around about the list of commands. Ignoring the Jupyter Labs misspelling, and yeah, this is, so there's like the directory stuff, creating a directory and moving the archive into that separate individual directory. If you go past that, then you can move into that directory and extract that archive inside that directory. Then create the virtual environment, install these 3 modules here. And if you're there, then you should be ready to go as far as setup wise. So yeah, now you can start a lab with Jupyter Lab, and this will create the sort of Jupyter kernel as well as open up your web browser to your localhost web server. By default, it is it serves the website only on your 127.0.0.1 interface, so only on your local host. So you can only access it from that interface. You can't access it outside of the machine. Important safety measure there, because of you don't really want to host code execution to like AUEHC or something. So yeah, once you do this, it'll open up a web browser and pull you to the page, which is your local host, which is, man, I need to like figure out how to scale up. So you know how to like scale up Firefox in a, I tried. Control plus. Oh yeah, perfect. Control plus, not Command plus, because macOS has 2 control buttons.
Was everybody able to get it up and running?
Yeah, that's, and we're like not super strapped for time. So if you guys are having issues with setting something up, we could stop and wait if you want to follow through. But yeah, so that'll open up this. If you're here, you're at a good spot, or you've made it through the setup stuff. But so let's see. So I was going to go through the notebook solving the puzzle we started last week. That was solving a substitution cipher. If you sort of remember from last week, we sort of got into it, and then it became a very involved process, as cryptography, CTF puzzles tend to do. And yeah, it's not like, or it's not a, they can involve some Python that's beyond a few lines and so on and so forth. Particularly like the more interesting cryptography challenges take, a good bit of time to solve. So this has that sort of solution laid out, but we can sort of step through it and go over the process, I guess. So yeah, there's like some setup stuff, just importing and reading in the ciphertext file that we had, which was just binary data, pretty much. It's binary data, but as we'll see, not exactly like random data, which is the key sort of distinction. And yeah, so we had gotten so far as like counting or actually looking at the character frequencies of this. So like counting up each byte and plotting out its character distribution and comparing that to like regular English and figuring out, what it looked like. So in this case, yeah, this is just a function of what we had, which is like count up all the bytes and display each byte's frequency in the ciphertext. And there's some very odd-looking frequencies here, as far as a super spiky single byte near 100, and then another, just overall a distribution that's far from uniform. As far as, and there's probably a way to like maximize this so that I don't have the like, that's a good question. Nothing at all. There's a view thing. Show left sidebar. Okay, that's a little better. How's the like? Okay, yeah. So you can sort of see the text and stuff relatively well. The text is not important for the interspliced literate programming markup style that IPython Notebook has is not super important for here. Is more if you want to like go back and follow through it later and figure out what it's doing. But yeah, so we had up to there as far as like plotting the frequencies, and then we'd sort of figured that a good way to kind of guess what the substitutions were was to look at a known reference text from like an English book or something, and go off of that and match the most frequent character in that with the most frequent character in the ciphertext, consider them to be the same character in the plaintext, and sort of infer from there what the key was. Yes?
What were the, on the graph, what were like the left and right values? Or like
Oh yeah, the min and max? Or
well, like on the bottom, it has like 0
yeah.
through 200.
So the x-axis here, and I should probably have labeled these. The x-axis is the byte value itself, so from 0 to 255.
And that's in decimal, not
in decimal, yeah. So 0 to hex FF in binary or in hex. And the left side is the relative frequency in the plaintext. So that's just the percentage of, or the fraction of the plaintext that was that specific character. So it's the number of bytes divided by the total number of bytes in the plaintext, or sorry, in the ciphertext. So like the character that we consider to be the space character, or the byte that we consider to be space, was like 0.15 of the 15% of the overall ciphertext, basically. So that's what the y-axis is saying. And yeah, we were sort of, you could pull up the frequency distribution of the English language and look at that. The sort of telling thing about the English is not so much the like maximum, like all the vowels which appear, or vowels and common characters like T and S and stuff that appear very frequently, but also the specific collection of characters that are rarely used, like Z and Q and X. Those are the sort of right tail of the distribution is very infrequent. So that's kind of a big tell of like, and this one has a bunch more of those rarely occurring characters because we sort of assumed, or we figured that they were more, or that it contained like capital letters and punctuation and stuff. Since we're sort of taking we're mapping it to like 256 bytes. Our character set is not just the 26 letters, but also the capital letters, punctuation, and other stuff. And yeah, so here's the sort of function or here's the like code block that downloads the sort of known English text that we were using. So like in this case, grade expectations, which is, I have like a code block to download that if you want, but if you already have it on the machine, if you're using the tar archive, then you can just open it directly from the file that's already on there. Yeah, avoid putting stress on Project Gutenberg's servers. But yeah, so now we have our English, and we're going to sort of measure the frequencies there. So this is doing the same thing, but with the known reference English text. And we're looking at sort of the, obviously the space, which is hex 20 or byte 32, is round about 16%, which is where our expectations were. No pun intended. And then the very cluttered distribution around the lowercase ASCII range, which starts at 97 decimal and goes up to 97 plus 25. Yeah, that's sort of the lowercase letters that we're looking at, and then these sort of low frequency capital letters and stuff. Yeah, that definitely aligns with sort of what our ciphertext looks like. So we can go from there and just kind of assume that our ciphertext is a one-to-one substitution between, or is sort of this type of English text that's been one-to-one substituted with the bytes that are currently in the ciphertext. So yeah, I should give some instructions on Jupyter Notebook's usage, because they're sort of, the way it works is like each of the code blocks are kind of separate and atomic. You can execute them as a single unit. So like function definitions and stuff, you can put in a code block and just define them there, and then they're sort of, they exist in the kernel memory throughout the time that you're looking at the notebook. So the way you execute code is you can click on it and click this run button, or like Control Enter is sort of the keybind that makes it easy to work with. So yeah, this is just sort of, as we, if we want to compare the distributions further and not have to worry about this being super cluttered here, we can shuffle around the x-axis on this and look at it side by side with the ciphertext. So taking these bars and just shuffling them and not doing anything with the height. And that's, yeah. But I think we don't need any further convincing that they're essentially the same looking distributions that we're dealing with English and so forth. So yeah, now on to the actual like substitution part. How do we go about figuring out the key, so to speak, or inferring the like actual substitution that was made to create the ciphertext? We could do that. Match frequencies stuff that I was talking about, where look at the top frequency in the ciphertext, or in the look at the top frequency in the ciphertext. Consider that byte to be the substituted byte of the top most frequent byte in the plaintext. So like when we see space in the plaintext, look at the most frequent byte in the ciphertext, which is like 100 and something, and then swap 100 back with space, considering that to be sort of our space character. This is probably our E character, so we swap that with whatever character. Wait, yeah, I've shuffled the. Yeah, this is the original distribution here. Yeah, shuffling the x-axis is a bit confusing. So yeah, this is sort of the E character here because it's so you can see A starts here and then goes up to E. So we match that and sort of swap it with what we had, and that's sort of what all of this handles. And then additionally, there's a sort of substitute method that takes in a mapping from the characters in the ciphertext to the sort of guessed characters that we think they map to in the original plaintext. So using our sort of guessed key from matching up the frequencies, we can see what it actually looks like. So yeah, that's what all of that is doing, and then we can see what we get out of that. Once we align the characters by their frequencies and look at it, we get some nonsense, but nonsense that still looks like it could be English. Particularly, the spaces have matched up well. I mean, that looks like the relative word lengths of English words, and there's a couple of words that like capital I appearing on its own is sort of telling that we've gotten something, at least. Y in U is kind of close to U. Yeah, you can look for, let's see, what else is there any sort of other sections that look close to words? Okay, so we probably got I and T right. There's ELLIC, which so now we can kind of look at words that look almost like English words, but or differ in like a certain letter, and we can go from there and swap the letter. Just basically swap the letters in that guessed plaintext and see if we can get to get back to the original plaintext from that. Because when we're swapping letters, it might feel like we're sort of conjuring the plaintext that we want to see, or like if we see AEL and think that's EL, and we swap A with Y, or T, if we think yeah.
So like, so this way you kind of jump in ahead a little bit.
Oh no, yeah.
Where it says like kind of in the middle where it says like capital I and then a re, like could that be like IC?
Capital I and then re. Oh yeah. So that's IC. Yeah. So we could switch R and S, and we would still maintain the one-to-one or the original. We would maintain the positions of the the substitution with the original ciphertext. We're not sort of creating this message so much when we swap it, because we're basically just changing up the original mapping that we did to get to here. We're just changing those two characters and what they eventually map to. So yeah, that's what this does, is just take the text that it's given and then swap all occurrences of byte A with all occurrences of byte B. So we can use that to sort of, let's see, we were swapping R with S and see how that looks in the result. So see if that looks anything a little bit like, and I forgot to execute these as I went down. So yeah, one thing about these is they do sort of assume a top to bottom execution order because they need, or because certain things will depend on functions defined in the previous block. So yeah, that's executed now. So we have our swap function defined, and we can swap R and S. And let's see, where was that IC section? Fourth line down. Yeah, I see. So yeah, I see. Yeah, there's R now. I see. What else? Involving an R and an S now looks more close to English, or close to English. So yeah, I agree. I think that's. O and S, yeah, that might be. OT. So wait, I see OT as well. I think so. Yeah, yeah. O is a standalone letter, which is definitely an indication that it should be an A. That's yeah. So we can take. So we've already created our new guessed plaintext from the swap, so we can keep just swapping letters here. So O and A, swap those so that we get. Whoops. Or so. The A's definitely look more. So yeah, we did ruin the ARE thing. But what's a 3-letter word that ends in E that appears so often in? Yeah, that ends in E. Yeah, THE would be my guess as far as what that ORE is, because there's also these OELLs, which are. Seems like we should swap O with T and see where that gets us, I guess. All right, so that's looking a little bit more. There's the word estates, so that's would be an unusual pattern to appear from random. Mainly, yeah, that mainly. Let's see. We could, let's see. Yeah, the eyes is positionally swapped. That's yeah. We can't change the positions of them because that then messes up. That would be the more messing up things. Said. Okay, yeah, it said did, yeah. Yeah, that seems right. So we have D in the right spot. Let's see. TC.
I see 2 YNUs.
YNUs. Okay, so let's swap in O then, because that'll. Let's see. YNU. Yeah, swap N with O, so we get U. That's probably. Okay. Yeah. 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 So now it's looking like legible gibberish. ESSION. All of the IOU or IONU stuff that we swapped looks like it's in
the bottom right, like it says like cap or like U and like dog. Should the G be W?
You know. Let's see, where is it?
Like above your cursor, right there.
Down.
Oh yeah, you know. Yeah, that's it. G is definitely W. It's still U. Okay. Now it's. What else do we have that's standout-ish?
Right above where you just changed, it says something did not even, so it might be even.
Yeah, B and V. And notice how these are like B and V kind of similar in occurrence to the or the letters that we're swapping are kind of similar in occurrence in like normal English. Like we're not swapping like a Z with a E or something like that because we've kind of aligned them with our reference text to start with. So now we're just moving from there to what the actual substitution was. So there's like, that's a particularly so wait, what did we just swap? G or something like that. But that looks like a particularly
Is this CU? You said not you.
yeah, see you tonight, yeah.
There's also a today is and then Wednesday, or that's what it looks like. But you can see it's towards the bottom.
Today is Wednesday.
Oh yeah, I see.
It's got a dash for W.
Okay, yeah, that's
a pretty obvious one.
dash replaces with W.
That's kind of interesting.
Oh, it might be a capital.
Yes, capital.
Yeah, that would make sense because dash is a pretty uncommon character, and capital W is as well. Where?
V is an exclamation point.
For V, yeah.
The character V?
The lowercase. Well, see, you've got today is Wednesday, and then there's a V on the end of it.
Or unless you think it's a period.
This would be the type of exercise that this would be the type of exercise that like NATO phonetic would come in handy. But V, do you mean V as in like Velcro? Victor? Yes, Victor. V and exclamation. Is that right?
No, V is in boy.
B is in
Bravo.
Yeah,
Bravo,
yeah,
okay.
yeah.
Okay.
Exclamation point, period.
Yeah,
It could be
exclamation point or
exclamation point, it could be period. I mean, once you see what happens, you can.
Yeah. Oh yeah. We can also swap back if we make a mistake because we can just
You still need to change
apply that
R,
again and get
you
the
still need to change R and H.
R and H. Yes. Yeah, that's a yeah. There's a lot of AHEs in there. R. Let's see. There's yeah.
M and F. I see yourself.
M and F had grown old and okay, yeah. Common M.
Or actually,
Yeah, because that'll get morning there, comma morning.
my friends,
Okay, yeah, there we go. I see.
Is C in space?
Let's see. C looks like something is. I see what's going on, or I see the issue with C. Look at where our new lines are occurring.
Oh, is it like a new line or a
Yeah.
convention?
Yeah, you see like RE something EPTION. That seems like that should be a. Let's see. So that's what hex OA replace with, and I think it could just do new line replace with C. And yeah, there we go.
Capital S, capital B. Look at the first line.
S and capital B, like that.
Yeah.
Oh, yeah, the Bonapartes. Yeah, that's it. And we could probably, from this point, figure out what the actual text is and go from there. But the one thing when you see a lot of these sort of cryptography puzzles is that like there'll be a huge block of text, and then the actual like answer here being AUCTF something. Okay, yeah, we've actually got the full answer there, but yeah, basically the answer is just kind of hidden away in the actual lorem ipsum style text or whatever that you're using. So like this hex AB thing is probably a left bracket as the sort of AUCTF flag format typically is, and then we've got like a oh yeah, D and what was it, capital D, and anyways, we could go around and like solve this until it looks right, but here's the actual text printed in its encoded, ASCII encoded form. So rather than, decoded from the bytes to regular ASCII. Flag is, I'm guessing that's a quote. I say I'm guessing, I made the thing, but capital R quote. So yeah, I think that's got the flag. Rebuilt that.
The reason there's an R in front of AUCTF.
Yeah, it was the quote there. Do you see it? By the way, let me know if anyone says anything on the Discord chat. I don't have it open on my laptop in case messages come up, but
What do you think that double, like it has two D's right there?
I don't actually know.
You may have mistyped.
Yeah, that might be a mistype. Because our D is correct in as far as ground. Wait. Oh yeah, that's Q is a capital D actually. Let's see. Yeah, done. We've gotten the D substitution right, and it shouldn't be, or maybe. Oh, I know. The right bracket didn't appear in the original or in the reference ciphertext that we used, so it stayed its original form when we did the swaps. So the known English reference text that we compared the ciphertext frequencies to didn't have a right bracket at all. So the right bracket was originally encrypted to D, but then when we did the swaps back around, it left it as D as well. So that should be yeah, I can't change it, but that should be a right bracket in the flag format. Yeah.
If you scroll to the very top, or to the top of the ciphertext,
Yeah.
another trick you can use on a lot of these is people are lazy.
Uh-huh.
I don't know who this is from, but
Oh no, this was put together in a rush, so I would imagine people were lazy.
So if you actually start, once you get enough words that start making partial sentences,
Yeah.
you can just go find where they stole it from.
Yeah.
This is at least that first paragraph is War and Peace.
Everything but the flag down at the bottom is War and Peace, yeah. This was yeah, not stolen, but generously provided by Project Gutenberg's public domain.
I didn't mean it that way.
Yeah.
But like at the top, once you start getting into like complete phrases,
Yeah.
the family estates of, well, something. You know,
Yeah, it's.
I found it by googling Genoa and Dust family estate.
Yeah, especially when it's the opening line too. It's very easy to OSINT your way around those sorts of puzzles.
Conversion really easy when you
Yes,
what
because then you literally know the ciphertext, or you know the plaintext. And once you know the plaintext, substitution ciphers don't hold up to known plaintext attacks because they're one-to-one transformations between the letters and ciphertext. So yeah, that was the sort of puzzle there and the process about, or a process, not the process, about going around and solving it. The other one, if I can bring the side thing back. So yeah, we were going to sort of shift back into Zor ciphers, since they're tangentially related to, I mean, they're a subset of substitution ciphers, I guess. They're kind of behave the same way, but they provide useful properties for building actually decent block ciphers and, well, stream ciphers as well out of when it comes to masking structured, whatever data you have with some sort of stream of random bits. And this is kind of a demonstration of both the benefits and pitfalls of just plain Zor ciphers. And let me show left sidebar. Stop that. So yeah, additionally, some like setup and stuff for this one is just importing the Python image library, which we installed as a module inside the virtual environment. If you run that and it says PIL not found, then that's the issue there. And then there's also a image called caterpillar.jpg that's contained in the archive file, so you don't have to go and download it from Wikimedia. But if you wanted to, or if you wanted to change the images out, you could do that with a different URL using the URL lib, basically wget. But and this will also display the image in line so we know what we're dealing with. And I chose a very large resolution image, which is not ideal for this. So if you happen to run out of memory executing stuff, particularly because it goes through and XORs every single pixel in the image, every single RGB value of every pixel in the image, that's not the best way to, or that Python's not great at that. So if your notebook kernel crashes, that might be why, and you might have to downscale the actual image that we're working with. So yeah, that's the image, and then these are just some Python functions for doing very high or very complicated operations in a very high level manner. So the first one is take a image represented by 3 tuples of red, green, blue values for each pixel, and XOR each pixel with, so XOR the red, green, and blue values with 1 byte in the key, and then move on to the next red, green, and blue thing, and the next byte in the key, XOR the red, green, and blue with that 1 byte, move on to the next, XOR the red, green, and blue with that 1 byte. We could have it be like each byte of the key XORs a separate RGB value, but this just makes more sense visually as far as like treating each pixel as a unit. But that's what that does in 1 line. And the other one, so XOR image is like, it is a wrapper around XORing bytes, and it just handles the taking a Python image library image object and converting it into that 3 tuple of RGB values, and then converting it back. So XOR image and XOR bytes are just taking an image and XORing it with the key over the however long that key is. If it's a 1 byte key, then we XOR it. Each byte XORs with, or the 1 byte is just XORed over every single RGB value in the pixel. If it's like a 3 byte key, then start with the first byte on the first pixel, start with the next byte on the next pixel, start with the third byte on the next pixel, and then wrap around back to the first byte on the pixel after that, and so on and so forth. That's just the basic sort of XOR cipher thing from 1 bytes all the way up to a one-time pad at the length of the actual underlying data. Although this isn't technically a one-time pad because we're also using each byte on separate individual pixels, which would probably reveal some pretty, anyways. So yeah, and this is for when we get down to showing XORing 2 images together, and what does that get us? You'll see why this is declared later, but it's essentially the same thing, just without using a key, but using XORing both the images together. So yeah, now let's just take a single byte XOR key and encrypt
What were you what were you supposed to do if the kernel died?
If the kernel died.
Somebody had a kernel die.
That would be, let's see, let's find a,
Did anybody else in here have their kernel die?
it might be the case if you're working on something with small bit memory. One way to work around it would probably increase the limit on memory that the Jupyter kernel has. The other way would be to find a smaller image. So let's see. Find a caterpillar image that isn't so.
What size image is that?
It's like 4,000 pixels. It's like 4,000 by something. I thought it would look cool in like high resolution.
It looks really cool.
It looks cool, but it's also high resolution. So let's see. This is a sort of what looks like a. I don't actually know what the. Yeah, okay, that's a relatively small image. So rather than using, this was at. I just Wikipedia Google or for. I mean, you could use any image you want, but or well, any red, green, blue image you want. So like a JPEG or something that's got colors. It depends on like the actual image mode, whether it's black and white or whether it's RGB. But yeah, you know, finding a picture like this on Wikipedia, copy the URL there, and then put it in request URL retrieve is the Python way to do wget. So put it in caterpillar 2.jpg so we don't overwrite the original file. And import URL lib if you're going to do that. And let's see. Let's open, instead of caterpillar 1, let's open caterpillar 2. See what that looks like. Cannot identify image file. Did I misspell it? I did. I misspelled it twice. No, that's right. Did I not get the URL right? We're locked in now. Request.url retrieve. URL equals that URL. Do I have, let's see, did that correctly, let's see. Open up a terminal. If I can navigate around that. New window. Demo. What is the, I don't want to open my file system. What's the way to like display a file in, or like, yeah, EOG's GNOME. Open? Okay. Could not be open. Damn it. I must have, yeah, damaged the, yeah. Okay, I gave it the wrong link. Which is unusual. Did I not copy the full thing? Because that's the... Okay, whatever. I'm not going to Google Harry Caterpillar. There's a Wikipedia link, and that's upload.wikimedia.org. Okay, and that looks reasonably normal resolution. So let's go with that one. First, let me lib. Well, let's see.
You just need to put it in the archive section.
For the, yeah, if you have an image, you can just put it in the local directory and specify it by name, rather than trying to like wget it. But
You also have the code in there to pull it via URL, right?
yeah, you can just replace the URL in the code here with what you have. But it looks good in the in all its glory in what 4,000 by I think it's like 4,000 by 2,600 pixels. The original Caterpillar, so let me just go with that one. And although it does take a little bit of time on my computer. But yeah, if it's on like a restricted memory VM or something, that would be why. So yeah, we've defined all of these, and it's also on like a florid of broccoli, which is kind of cool. So yeah, now using a single byte on the image, what do we think that does to the underlying like pattern of the image itself if we're just XORing each pixel by the same byte repeated? Particularly thinking what we know about like substitution ciphers and how they always swap the same byte with the same byte regardless. Yeah, encrypt the image, but like, oh, invert, yeah, like negate, image negation, I guess. Take, particularly if the key is something like, well, yeah, basically, you know, if the key isn't like hex 00 or something, so that it returns just the original image, yeah, if it's something that like flips the bits almost, it's going to look pretty much like an image inversion. K is what, like ASCII 4 something, so I'm going to actually draw a different, well, that's only a couple bits. It might work. Let's try it. And again, yeah, XORing the entire image in Python when it's large takes a little bit of time. But yeah, looks like a image inversion. It does nothing to like the underlying message as far as like, you know, you can do the same thing, the same sort of frequency analysis type stuff and figure out what the original, I mean, to some degree, what the original message was. We certainly can know the meaning of the original message just by XORing it. But so if we try and like increase the length of the key and do like a, in this case, 1,024 bytes instead of, so using a random 1,024 bytes as our key, which is already by modern standards a massive key, but it'll do a better job of like masking this sort of structure of the image by the randomness of the key. But the problem is the key repeats after we get to like the 1,025th pixel. We start over there, and so we mask that section so that it looks pretty random. But then we get the problem of now we have the repeating pattern of the key, and that's its own sort of structure that we can use to see like the almost more, oh boy, pronouncing French is not my, MOIRE pattern of the Moire pattern, I guess, of the repeating 1,024 pixels as it goes across. And you can sort of still distinguish, you know, what isn't like the background of this image and what isn't. And you could also like, I mean, that pattern exists even though it might not be human distinguishable. It's certainly like distinguishable by looking at the actual byte patterns themselves. It's computer distinguishable at least. So yeah, and we can extend that up until we get to a one-time pad, and we make the key the entire length of the image. So we make the key the total number of pixels, and ignoring the fact that we're technically XORing each byte of the key with 3 underlying RGB values, and that would break things. What we get out of this is a very random looking random noise, because we're taking a cryptographically secure significant amount of random key bytes and putting them into the key, and that kind of does the job of like masking the underlying caterpillar structure of the image. That pretty much obliterates any sort of pattern that we could use to, I mean, this makes it indistinguishable from random, so there's no, because of the nice properties of Zor and its ability to essentially take the randomness of something and mask it, and mask some underlying like image in this case. If we were to encrypt that, again ignoring the underlying problem of Zoring all the RGB values with the same byte of the key, we would encrypt that and send it. If we could recreate that key on the other end, we'd have, you know, a perfectly indistinguishable random blob to send across the wire that would, you know, there's no pattern to be able to use to do anything other than like brute force the massive key at this point. Because, well, yeah, there's no brute forcing there because you could recreate any sort of image out of this if you wanted to by trying to brute force. So there's just nothing to go off of. And the other nice thing about Zor is that it's applying the same Zor operation over again returns the original input. So when we Zor the image again with that one-time pad on the other end, and this is why it's sort of classically used as a sort of bare bones cipher, and also very common in like CTF type challenges, is because of the fact that we can recover it with the original key just by Zoring it. So taking the image, Zoring it once with the one-time pad returns this, and then Zoring it again with the one-time pad gets you the original image. Now, some tricky or sort of consequence of that property of Zor, and kind of any sort of sequence of operations where you Zor that one-time pad in and then re-Zor it later with the one-time pad will return the original, will basically effectively cancel out that Zoring operation. So if we were to reuse that one-time pad, call it a two-time pad, and Zor this image of a butterfly, which also again is massive, and resize down to the, you could actually just use image.resize to resize these to like normal resolutions by passing in, rather than that, you could pass in like resize both to like 1920 by 1080 or something. That would actually be another way to do it, because this handles the like downscaling for you using like a standard default method. So this resizes the butterfly down to the size of the caterpillar. So here's the other image that we have, and we're going to Zor this one again with that same one-time pad. And what happens when we Zor the encrypted caterpillar with the encrypted butterfly? Given what I just talked about, the like sort of repetitive applying a Zor operation anytime in a sequence, anytime in a sequence of Zors will cancel out the original time that it was applied. So if you reach for the marker and it's not there, so the caterpillar is X, Zor the key K, and then Zor this with the butterfly, which has also been Zored with the key K. These sort of cancel out. What do you get? So what do you think that looks like in terms of pictures? We're about to find out. So this is Zoring both of the encrypted images together that were encrypted under the same one-time pad in slow fashion.
Yeah, that command used like 5 gigs of memory.
Really?
Yeah, that's why my VM was crashing.
Okay, that's that would slaughter any VM. Why is that?
I had to give it 8.
Okay, I mean these are like, on the order of 100 something megabytes, but geez. So yeah, something about list constructors and probably temporarily storing the image several times over. Yeah, so there's our butterfly zored in with the caterpillar, and I think the the caterpillar's background is
Black. Just straight black.
black, so it
that's
doesn't.
why it's all the butterfly background.
Yeah, which would be the absence of RGB values. Yeah, so that would be zeros. So that's why it's that's cool. Anyways, so yeah, that was basically just a demonstration of Zor being useful for its ability to, and what are we as far as time was? And I was gonna go into like S-block stuff, sort of tie that into building or like combining those like Zoring, Xboxing, or S-boxing substitutions that are nice and nonlinear. I could go into that briefly, but also like there's another sort of puzzle at the end that will take probably 40 minutes, and we're now at this. So would you guys rather do like a puzzle-y thing with the other notebook, or go into this S-block stuff? What? Leave it up to the people here or people that listen on sorry, or the people that are on line. What sounds more interesting? I'm partly thinking we just go straight to the puzzle.
What are the components of the puzzle?
It's a advanced substitution cipher, of which. Okay, let's do the puzzle. So yeah, before I get through this, because yeah, I think it'll take us it'll take us like the full time we have left to do the puzzle alone. So, and I think it's more interesting than doing the other thing. You can like section these out. So yeah, this is if you go to mockctf, this is like the shifty schwoozy problem on mockctf in crypto. If you're on Auburn's thing, if not, you don't need to VPN in to check it out. All the the ciphertext is included in that archive, in the tar ball, and yeah. So this is kind of applying similar techniques from the original substitution thing to solving this puzzle due to an author goes by the alias C. I'm not sure who that is. But. So, yeah, as with the other one, and I don't have like the text here, so it's actually easy to see. God. Right sidebar, left sidebar. Okay, so like as with the other original thing, we see this. I should have printed it here to see what the ciphertext is. Let's check the first 1,000 bytes or 1,000 characters. So, yeah, we get this gibberish-looking ciphertext. It looks kind of like what we had after applying the sort of initial guessed substitution from the previous problem. But yeah, let's go into more frequency analysis stuff. So doing the same thing that we did earlier, just count up the relative frequencies of all of the characters and look at them. So in this case, we're working with an ASCII file rather than raw bytes. So rather than counting up all the 256 bytes, there's only printable ASCII in this. So we just map or plot each actual ASCII character with its relative frequency. So you can see the space character is obviously the space character in this one. What does that imply as far as the space character looks very much like what we had these capital letters down here look very much like what we had as far as their occurrences in like the plain text. These frequencies are all off as far as that, but like the space shouldn't need remapping in this. I mean, it does look like English word lengths and stuff. So I don't think we're like all swapped around here. There's some sort of like a cipher that preserves the comma is there as well. Capitalization, it preserves punctuation and capitalization and stuff, which is anything sort of neat about that as far as when it comes to, does that give us any hints as far as deciphering this? Particularly with word length and stuff. Does that maybe tell us anything about the...
That would decrease like the overall amount of possibilities.
Oh yeah, definitely. I mean, especially if they were, yeah, that would significantly reduce our search space for like if the spaces were jumbled around and everything. I mean, if we can reduce the possibilities from looking at like all of these characters here to looking at, let's see, skip ahead to this extra block and then I'll come back and say what these are doing. So looking at only these 26 characters. So that's a huge, reduction in having to deal with stuff, which is nice. So what I've done is essentially reduced the plain text from, I've made it case sensitive, but remembered where the original capital letters were, as well as the original punctuation letters, so that we can take the like meaningful letter stuff and then go back from that, operate on that, and then transform back to the original structure of the text and preserve the punctuation and stuff when we get to the end. What do you think this is? Yeah. If there's a single letter like that capitalized, you could also do like a single letter that's lowercase and consider that an A and that sort of thing. So these are very, just the fact that it's preserves the capitalization and stuff is a very big tell as far as, hinting to what the actual plaintext is, especially if you can, it's pretty helpful for substitution ciphers at least to know even just one character in the plaintext to go from that and figure out what the actual substitution is. So so we plot these frequencies and those don't look like a substitution cipher or those don't look like direct English. So this is back to the other distribution of those, grabbing the Great Expectations text and then checking the distribution of only the like initial, or only the 26 letters in that. So rather than like we did all of the bytes in the original one, if we try just the 26 bytes or 26 characters here, letters, I should say, basically check the frequency of that using our same sort of throw out all the punctuation, throw out the capitalization stuff that we did with the to get this plot here, and we get that, which is more English-like, particularly the lack of X, Z, Q, even J. J seems off, but yeah, the the infrequency of these characters are the big sort of tells there for like, Z, or this is actually in the order that they appear, but Z is not that frequent. X is, I mean, maybe it's slightly less frequent than the others, but it's still mostly uniform. But it's not as uniform as we would expect if this were like some, proper cipher, I guess. If this were a much harder problem, these would all be like essentially flat lines, but they're not. And this is the part where I should explain what a visionaire cipher is. I've looked up the pronunciation for it. I don't know. I only know what it is. Yeah,
It's French. So.
Yeah, it has the guttural R at the end. I'm pretty sure, and I'm not gonna try that. And the what did you say, Vignere? That would be a good it's the whatever that cipher. It's a sort of one of the probably more famous classical ciphers. So like the pre-computer age ciphers that is basically a sequence of substitution ciphers. So the first character is, so you're given like a key of a certain length, and the first character of the key is swapped with some other character, and then the next character of the key is swapped with based on a different, all right, let's see. So the key itself is not, in substitution ciphers, but it's actually in letters, and you use that to create a substitution out of. It's the sort of very useful, or each of the individual ciphers are not only substitution ciphers, but they are shift ciphers. So if the character A is shifted down a fixed number based on whatever the key is, a fixed number of letters to like the character, I guess it's kind of nice to walk through as an example, but if the character A is shifted down 3 letters, or shifted 3 letters according to like the modular arithmetic of the English alphabet, then the character Z is also shifted 3 letters. Basically, you take whatever your key is, you consider that a number mod 26 based on its order in the alphabet. And then you do the same thing with the plain text. For the first letter of the plain text, the first letter of the key, you shift it down by whatever the mod 26 value of the key is. And I say shift it down because I'm sort of visualizing it as this table here that's very famous as far as if your key is A, you map A to A. If your key is B, you map A to B. A is essentially 0 mod 26, so A gets mapped to whatever the key is. B is added to B becomes C if the key is B, so on and so forth. It's like modular arithmetic but with letters, and that's what each individual shift cipher is. But the key itself is typically a sort of memorable word that, memorable being the keyword, that denotes the shift at each particular position. And then when the key repeats, so doing the same thing that you do with the XOR cipher, if you have like a 5-letter key, and there probably is a example here. So if you have a 5-letter key, it repeats again to start over. So A plus L comes to L, T plus, and if this were some other letter, you would still do the same plus L thing. The main thing about that is it's much less memorization than memorizing like an individual substitution cipher for each letter at the cost of now you reduce the total number of possible substitutions that you could make down from like 26 factorial to like only 26 at each point in the key. So it makes things significantly more structured, but your key is so the key is manageable and not like 20 or not several sets of different mappings for each letter of the alphabet down to that. I know that's like a poor sort of way of condensing that down because that sounds more complicated than it is, but it's the main point is that at each point here, for each letter of the key defines its own independent substitution cipher. That substitution cipher just happens to be a shift cipher, which makes things much easier. But yeah, so if we want to look at this and say, oh, this is a, if we were to sort of infer maybe by the name or maybe by the fact that it's like the top level challenge or whatever, that this is, you know, the classic Vignère cipher. One way we can detect that is, so obviously at byte 1, our distribution, or at looking at each character as if it were substituted by a specific byte regardless of its position in the ciphertext, we don't really see anything. But if we use a Vignère cipher with a specific key length, then each of those kind of decompose down to an individual substitution cipher. So if we check the frequency distribution by splitting our ciphertext based on a guessed key length, so in this case, if we guess that the key is just 2 bytes, so the first byte, so every even position character is substituted based on some substitution cipher, and every odd position character is substituted based on some substitution cipher, we can sort of see if those even and odd characters both separately decompose into what looks like English distribution, English character distributions. And they don't really. So that was sort of part of the process of doing this, is really inferring the key length. And because if you sort of notice that like the repetitive wrapping of the key is kind of similar to Zor ciphers, a lot of the same stuff applies as far as if you have a multi-byte Zor cipher and a multi-byte or a multi-character Vignère shift cipher. They sort of generalize to this same concept of like break this down into multiple substitution ciphers, I guess. And yeah, and I'll go ahead and like spoil it. We need to go significantly higher for this. So let's jump up to 16 and see what we get. 16, let's try 18, and nothing. The process of like actually finding this was like, yeah, none of these look really English. And then you hit 19 and you get 19 different character distributions, and they start looking pretty, I mean, let's see, what was our original English right here? Yeah, they start looking pretty close to English there. Aside from, again, the sort of characters being slightly, you know, shifted. And the nice thing about this is that we can just find that shift number, or that shift value for, say, like, if we assume this is G is E, so E has been added by 2 characters, or 2 letters, so E to D to G, so that the key at this point is probably B, and that would make sense as well for like X has gone from X to Z, and it still has its similarly low frequency. Z has gone from Z to B, which is off. No, it's still kind of high. But yeah, we can find these sort of keys much easier than doing that separate process for substitution ciphers, where you just like match the distributions themselves and then go from there. Because yeah, things are more constrained when you're dealing with shift ciphers. So yeah, we get that the key length is probably 19. So now, these are just some sort of helper methods for doing that actual shifting operation using characters. So doing modular arithmetic on the alphabet letters, basically. Shift them down to decimal 0, add them mod 26, and then shift them back. And then we have a guess method, which is take in a certain key of whatever we want to guess for. So we're going to try and guess like 19 linked keys, and then see what the result is by shifting them down based on how they would have been shifted under that original key. So doing the inverse of the original shift plus modular arithmetic to just minus modular arithmetic to recover what we think is the original plaintext under the key. Now, back to past all of that mess stuff. What was the thing about, yeah, this and potentially knowing certain cipher or certain plaintext values if we know their, what's one nice thing about shift ciphers if we know one known plaintext character and one known ciphertext character, sort of falling back to we don't have to remember, or we don't have to solve the entire substitution thing. We just have to find the like shift itself. So if we find one character, what does that mean? Or if we find one known plaintext character in one specific position in the text, mapping to one known ciphertext character here. So if we assume that like this is I or something like that, does that? Yeah, if we know the, yeah, we know that shift offset. So we know that key for that specific position in the, we know that individual shift for that specific position in the key. So whatever this is in the ciphertext mod 19 or whatever, we can assume that's an I. I shifted to A is like 20 something, I don't know. So we can go back from that to the I and figure out what the key might have been. There's a bit of a challenge as far as ensuring that that was actually an I and not like a capital letter followed by a period or something like that at starting a sentence, so a capital A. And it would probably be, in hindsight, better to just look for the lowercase a's. But yeah, so I have something that finds the uppercase I's based on, or the uppercase single individual letters, and then takes the sort of most common shift according to that position in the ciphertext and uses that to guess a key. So that's what these functions help with, and then, yeah. So we use those shifts of the I to guess what the key might be, and see what that key actually is, because usually when it's a Vignette cipher, it's some sort of memorable characters, and then we use that to guess in the ciphertext. And then the decompress function is just doing that original, recover the original punctuation and capitalization based on how it was in the original ciphertext. So just restoring all of that to whatever our guessed plaintext is. And I forgot to execute stuff, specifically this block. Okay, so we get this key here, which is COUS, I mean, has like this in it. Not quite what we wanted, and that was partly due to, well, you'll see in a second. But, you know, YHU, comma, VA had, let's see, I don't know. So if we wanted to sort of adjust this key, we can just So now instead of trying to like swap out substitutions and stuff, we can look at like, I say that looks relatively, or that looks in at, so we can like swap out a letter here and see what it does to the actual text. We change the I to that, so that's, oh, wait. What does,
How long of a key would you generate?
this is a 19 character key, because there were 19 of these. And I'm gonna skip some like of the sort of nitty gritty, like try this, or like try and figure out what, so this almost looks correct as far as like there's some sort of, this looks like the word understood basically, except is slightly garbled in the middle. So we have parts of the key, like the whatever part aligns with U, N, S, T, O, O, D, we have that right. But we don't have all of the key, and solve might help as far as switching the D and the thing. Yeah, that fixes the understood thing, because whatever those two letters here that were flipped were O, corresponded to the O and V in the key. And then, let's see, just before that,
Is that like, can you solve this?
yeah, can,
Yeah, like that says it out.
and I think the can, it's not can you solve this, it's can solve.
Can solve.
Yeah, that's cool. Well, I say that. Maybe it, wait, can,
Unless you change the original problem, it's not can.
okay,
It's also not 19 characters.
I was getting to that.
Yeah.
It's, the last one is problem, yeah. You had that right. So when you switch this, and do I still have the 19 characters right? I should, because otherwise this would be kind of obliterated. Why was I thinking it's you solve?
Yeah.
Okay, there we go. That's more whenever you feel blah, blah, blah. Yeah, so it's you solve this problem, and the problem now we have is that half of the ciphertext looks like it, or half of the plain text looks correct, half of the plain text looks not correct, which, yes, specifically 19 characters spans look very nice, and then the 19 characters immediately following that look like gibberish. The 19 characters following that look nice, the 19 characters following that look like gibberish. That has to do with sort of this process of how we guessed the key length there. Any sort of light bulb moments as far as what that might, yeah, because we've looked at these distributions of like splitting. Yeah, when you have a multiple of, so we land on not a multiple of the key, but we land on a divisor of the key, and split the plaintext based on into the half of the distributions that land on the key and look like English, then the half that don't land on the key that look like non-English, but we start back over. So we get mostly English-looking distributions with a few like oddities, such as some like Z and stuff appearing, or whatever we assumed, appearing more than what we had.
So you could do that for like any number or whatever.
Yeah.
If you had like a fourth or something like that, it would be like 19 times 4, and that would be the key.
Yeah, you would see they would get more muddled as the like. So when you're talking about that, you have half of a distribution that looks like English, or half of the character frequencies. You're talking about like one half of the, I don't know. As the key gets larger and larger, they'll look less and less like actual English. But yeah, essentially, it's another thing is when you see multiples of the key as well. That one's where you can also, you don't necessarily guess the exact key length like this, but you can sort of guess the multiples. And where was I with the, yeah. So let's try this with 38. And that, I will say, looks a little bit more like English once we go through it and split the ciphertext up and count 38 distributions.
It's like technically, like if you put 7 key length to 2, then a 19th of that would actually be correct.
Yeah. Yeah, it's tricky stuff. But yeah. And yeah, this has more of the like very infrequent characters that are characteristic of English. So yeah, it's a 38 length key, or 38 character key, and we only have half of it. However, as there's a nice trick to when you have solved partitions of the plain text like this, and it looks like some sort of English text, you can usually do a nice Google to figure out what it is. And I think there's a yeah.
That's all Gatsby.
Yeah, there's Gatsby, there's so you can know exactly what the plain text was. Let's see, let's find.
Back to the earlier discussion, if you have the plain text, the keys.
Yeah.
Relatively.
So we can find the other 19 characters of the key pretty easily. Let's see, what is it? That's where were we in the yeah. Whenever you feel like let's see, what's it? Unusually communicative or and after boasting, that's a good. Okay. All right, so we're at the start of in my younger and more vulnerable years. So instead of what was it? So now we just need to find whatever the shifts were from this to in my younger and more vulnerable years. So let me pull that down. Oh boy. So let's see, plain text equals in my younger and more V, and then ciphertext equals, and make sure I don't overwrite the original stuff. Let me do known, this is m at, and LC in, and I should probably go ahead and just reduce these. At LCN AZN AKM WKLY. Alright, so we can take every character in this and shift it down by plain text, known plain text, known ciphertext, and I did not. So control or shift clicking also executes apparently. For key equals that. For let's see. Actually, so wait, we can just do this by doing the shift inverse thing. By shifting the ciphertext down by the plain text, we so essentially trying to do that. So if you subtract, yeah, the key was added to the plain text, so subtracts the plain text from the ciphertext, and you get the shift inverse the CPN known plain text zip plain text, ciphertext, and yeah, you don't have to worry too much about what the list constructor does, but we're taking every key, every character here, and print recover known plain text, known ciphertext. We get that wrong. Let's see. Shift the ciphertext down by the for the order there. It's still wrong. Take each character of the ciphertext, subtract it by the plain text. You should get the key, right? Because you added the key to the original plain text to get the ciphertext. And let me known plain text, known ciphertext, and how are we on time? Oh, I'm glad I checked that. Yeah, I just saw the notification pop up. Let's see. Shift inverse the ciphertext minus the plain text for ciphertext and plain text for each character in the ciphertext plain text. Yes, I believe that's, and we still get what we had. Am I using the correct in my younger and more vulnerable, in at ML C and AZ? No, we weren't. Yeah, it returns A minus B. Well, I'm fairly certain that isn't the key. So ciphertext and plain text. So for each character, I'm just going to write it out in old school style. Yeah, I know the shift inverse. Let's see. Actually, let me do some debugging here for a second. Apologies for the debugging. Print assert inverse. Let's see. Subtract C minus Z equals C. Oh yeah, they're not really invertible there. Is that where I'm messing up? That they're not, you can't, if you subtract from, so you add the, like, each character of the key to the original plain text. Yeah, let's see. Shift C Z shift inverse. Okay, yeah. So if we shift C by Z characters, whatever that means, if we add 25 to C mod 26, and then we subtract 25 again from whatever the result, then we get the original character, which is what I'm doing here, unless zipping strings doesn't exactly pair them up pairwise letter to letter, but they should, which is where I'm like thrown for a loop. And let's see. If we're subtracting, wait, that's subtracting z from it, z. If we're adding some unknown value, say k, and we get the result of c plus k, and then we're subtracting the original wait. Do you not get the, if you subtract the plain text from the ciphertext, do you not get the original key letter that you used to add the, or is that where the issue is? Yeah, but you would still be able to like, yeah, if you add, as long as you do like the modular arithmetic on like the letters, so to speak. So if you take, let's see, C shift.
With negative modular arithmetic, you have offset by 1 because your negative 1 value is actually your 26 value.
We could like whiteboard this. I'm also, yeah, bumping up against time. Man, I wanted to solve this one. All right, but I think that's calling it, and then I'll post the. Yeah. Let's actually do that. This is the. Okay.
It's Gubala.
Gubala. Like that.
GUBALA.B/VA-solver.
Okay, yeah, I'll let people find that on their own and solve it. Okay. But yeah, the idea is, yeah, we still have the known plain text, and we know what it what the ciphertext was. We should be able to recover the key offset from that, and I'm just screwing up somewhere in my logic for doing so, possibly with an off by 1 error that's causing this key to be ever so slightly close to whatever the original is, but 1 off. I'll figure it out and post the actual full solution or whatever after that. But yeah, I think that's it for time.